Okay, so the next section is least squares approximation, another section in linear algebra. Okay, remember before we had this formula of y equals mx plus b. It's called a slope-intercept form. It's a way of using a linear equation to represent a straight line. So if you've got a lot of points and you draw a straight line through them, you can model that, if you will, by those two parameters, m and b. What happens, though, if you have a lot of points and they're not aligned, or really if there's way too many of them? So I'll draw that. Suppose you have a grid. You've got your y's and your x's. And I'm going to draw in blue a number of different points. So let's say I've got a point here and a point here. I'll just make a few of these. Okay. So I've got a whole bunch of x, y points. Now, if I want to try and curve fit or apply some curve fitting here, draw a straight line through, obviously I'm not going to be able to draw a straight line and hit all the points. But I can do something that tries to get approximated through the middle of them. So let's see if I can do that by hand. It's going to end up being something like this. And I'm going to do another color. This is great. I get to use all kinds of colors. Basically, what I'm showing is I've got a straight line here in red. I've got some errors here. This point is slightly off the red line, slightly above it. This one is way, way below it. This one is almost right on top. Way below, a little bit above, a little bit above, pretty far below, a bit above. OK. So if I want to come back to the point of y equals mx plus b, my model, then we can come in and say that the slope in this model, the m, is, again, rise over run. It's this x and y here. Okay, and then the intercept that we talked about is down here, the b. But we're introducing another thing. We've got some error here. We've got some residuals. The parts where the points didn't exactly line up. So we've got some errors. And those are going to be, here, let's use the green. All of these things. Where is it that the points didn't actually hit the line, and by how much? OK, so you have too many points. You don't have an exact solution, but you can approximate. OK, let's pull this into our case study of foobartender.io. We've got bartender ratings. So we do some kind of, survey at the end of an order, maybe to some randomly sampled people to find out how well do they like the drinks that got mixed. And we see how well our bartenders are doing by looking at those ratings. By the way, we spell bartender without an E on the end, kind of like Flickr doesn't have an E on the end. For startups, that's just a thing. The bartender ratings started out negative. When we first launched this business, we had some real bugs in the process. We had to get those worked out. But they've risen steadily. The company wants to run some ads now to leverage the fact that we're getting really good feedback, really good customer response. We want to leverage that buzz, but we want to forecast how well the bartender ratings seem to be rising. So the problem is we want to fit a straight line through the following XY points to forecast the bartender ratings for the next month. So we've got, initially it was negative, but now it's moved up and up and up and steadily increased. If I take and plot these points out, I've got 0, -1, 1.2, 2.9, et cetera, et cetera. And I can do a grid there of ratings versus month and show all the plot points. OK, and now I want to try and use some sort of curve fitting. So jumping back then a little bit, this idea of least squares approximation was introduced by somebody named Gauss. Actually, if I recall the story correctly, Gauss had a really good articulation of it, but I think that somebody else had actually described it earlier. But then Gauss went back and said, well, he'd actually used it years before. So a little bit of controversy amongst mathematicians in the 19th century. But something called least squares approximation was introduced in roughly 1809. There's a really great discussion on all the math involved in this. If you want to check out, there's a book that I'm recommending at the end of the chapter. It's called the book is by Gilbert Strang. It's an introduction to linear algebra. But I'm going to just go over some of the high points here. If we've got here our points, let's redraw this. Y equals mx plus b is what we're trying to solve for. Okay, and we've got ratings, and then bartenders, sorry, months. So let me go back to a good drawing here. Got ratings over months. We've got these different points. Let's see if I can do them by freehand. Okay. The idea is that we can define our xy's in a matrix and come out with something that looks like the form of ax equals y. We can come out with a matrix formulation, a linear equation there of a times x equals y. The problem is that we've got far too many x's and y's to actually fit with a straight line. We can't really get to this form, but we can try to approximate it. And the way to do that, coming back here to the slide, is we can take and multiply both sides of the equation by what we call transpose. That's basically we take a matrix and flip it on the diagonal. We can take A transpose times A. That's going to give us a square matrix. And we're introducing something x with a hat over it. So it's going to be slightly different than our actual x's. And then we've got A transpose times y. So we're taking our ax equals y, and we're going to work with approximated x's, x hat, and we're going to multiply both sides times A transpose. Okay, that's the big idea that Gauss was doing with least squares approximation. Now, another thing about this is to get here, we can say that A times x hat, we want to plug that back in. We're going to have a different vector. We're going to call it p. This is our approximation. We're going to say that p equals vector y, x's and y's that we got to, plus e, some error terms. So when we approximate, when we fit, we're going to have some error terms. Those are going to be in the e's. So effectively, we're taking y and splitting it into two parts, the p's and the e's. Another way to write this, we could say y equals that doesn't come out here. Sorry, y equals p plus e. And what we're going to try to do then is come up with a solution of p, having our solution, our parameters for a slope-intercept, a straight line. And then we're going to have a vector of errors that we try to minimize those errors. And the way that we're going to do that is by minimizing the squares of all the values in E, all the errors. So the least squares, that's where we get the name. When we take a look at this on the board here, if I can draw this well, we're going to approximate drawing a straight line through it. So you get the errors here. Again, error there. So we approximate the slope-intercept by minimizing the squared errors in E. You can see in the drawing here we've got our slope represented by P and the intercept, and then we've got the errors represented by E. And so visually, I mean, this is what's going on when you do the matrix math. To construct the matrix A, we're going to take all of the x values, put that in the first column, and then we're going to fill in the value 1 in the second column. We'll show how that works in a moment. And we take all the y's and we put them over into their own vector. Okay, now matrix A is not square. We couldn't get a matrix inverse on it. But if we multiply matrix A times its transpose is where you flip it on the diagonal, then you end up with a square matrix. shown here, you can see matrix A that I'm showing in a 2 by 2 would be square, but in something like this, it's not going to be. OK, I've got some Python, again, using NumPy. I'm going to represent my x's and my y's. I've got those in vectors. And then I'm going to build a matrix A out of my x's and put 1s in the other column. So let's take that. OK, so if I look at x, I've got the x values. If I look at y, I've got the y values. And then if I look at A that I've constructed, I've got the x values in one column and then 1s in the other column. All right. And now I'm just going to call least squares here under NumPy linear algebra. I'm going to call this function numpy.linearalg. The least squares function, I'm going to give it A and Y. And I'm going to come back with a number of different things. Here's my slope and intercept, my parameters m and b. That's effectively the p vector. And then I've got residuals. I've got the error terms. I've also got some other things that the least squares algorithm is going to give me. OK, and so if I print out, great. So I end up with getting m equals effectively 1, if you round that, and b equals effectively 0.95. The residuals that come out of this are 0.05. So I've got a pretty good approximation of a line. So if I want to state this again, I've got y equals mx plus b. I've got m equals 1.0. I've got b equals negative 0.95. OK, so I could say that y equals, well, 1 times x. So x minus 0.95. Now, if I want to forecast for the next month, let's say that x equals 4. So if I state this as y equals f of x function, I could say that f of 4, fourth month to forecast, that's going to equal to 4 minus 0.95, and that should equal 3.05, if I've done the math correctly. So our estimate for the next month is that the bartender ratings will be 3.05 in aggregate. Yeah, and again, the residual was like 0.05. It's mostly a straight line. It's a pretty good fit.